Hello and welcome to our lab on vector addition. A lot of times in the lab situation we're adding vectors, and vectors are measurements that have not only a magnitude but also a direction indicated. And so when you add two vectors together, you can't just sum them up unless they're in the same dimension. If they're all in the horizontal dimension, you can add them just like scalars. 2 plus 2 is 4, 2 plus negative 3 is negative 1. However, if they're at different angles, it doesn't work. You can't add them up like that. And so what we'll be doing today is taking vectors that are at different angles and then representing them with only horizontal and vertical vectors that we can then add up like scalars to get a total. Okay, let's start by defining two vectors. Now first of all, I want to define my coordinate plane. Y direction is vertical, X is horizontal, and all angles will be measured from the positive X direction. So 0 to 90 would be like this. Now, when we draw a vector, we always start with a point. This point indicates the beginning of the vector, and the vector is a certain magnitude. So let me draw one here. Let's say I draw a vector about 40 centimeters long. And this has an angle with respect to the horizontal. I'm sort of drawing a horizontal line here. And this angle looks to be about 30 degrees. So roughly 30 degrees. Okay. So there's my vector. 40 centimeters at 30 degrees up from the horizontal. Now if I want to add a vector to that, I want to start at the end of it. You always start the next vector at the end of the first one when you're summing these up in a pictorial sense. So this vector starts here. Let's make it, let's make it 30 centimeters in magnitude. So there's a 30 centimeter vector, and its angle is measured again up from the horizontal. So if this is the X direction, its angle is measured this way. And so it has an angle of roughly 135 degrees. So there are my two vectors. We have 40 centimeters at 30 degrees, and add to that 30 centimeters at 135 degrees. And so the sum of these two vectors, you can't just say 40 plus 30 is equal to 70. The sum of the vectors is a vector that goes from the very beginning to the very end. So it's sort of a vector that looks like this. And we'll call it the resultant, R. Here's the resultant vector. It looks like it has a magnitude of around, looks like about 63 centimeters. I'm sorry, minus 20, 43 centimeters. And an angle of about 70 degrees. So that's just kind of looking at it. Now let me show you how to get that resultant magnitude and angle mathematically. So to mathematically determine this resultant vector, here I'll go ahead and erase it to clean up the board a little bit. I need to add these two vectors together. And so in order to do that, I can't just say 40 plus 30. I can only add vectors that are in the same dimension. I'm going to make them either horizontal vectors or vertical vectors. You see, I can represent each of these with a horizontal vector and a vertical vector. Because if I start out walking here and I go horizontally and then vertically, I'll end up in the same place as if I went 40 centimeters at 30 degrees. So I'll break this down into two vectors. Now, you think, well, you're taking one vector, making it two. Isn't that making things harder? Well, no, because I'll also break this down into two vectors. Now I've got four, right? But these vectors are now consist of a horizontal, which I can just add together, and vertical vectors, which I can just add together as if they were scalars. So that's sort of the reason why I'm breaking these two vectors down into horizontal and vertical components, because then I can get a total horizontal and a total vertical, and after that apply right angle trigonometry to determine what the value and the angle of the resultant are. All right, so let's do a little bit of math. I'm not going to work it all out. I'm just going to set it up for you. This horizontal component is the adjacent side of this angle, 30 degrees. And so the adjacent side, right angle trigonometry tells us, is equal to the hypotenuse times the cosine of the angle. So the horizontal components are going to be equal to the hypotenuse times cosine of the angle. So let's add up all the horizontal components here. Our horizontal components are 40 times the cosine of 30 degrees. This one has a horizontal component as well. So we can add these just like scalars. That's 30 times the cosine of 135 degrees. And so the total horizontal, 40 times cosine of 30 is equal to 34.6 centimeters. Add to that 30 times cosine of 135, that's equal to negative 21.2 centimeters. And so the total horizontal is 13.4 centimeters. So let me write that out here. The total horizontal, I'll call it the x of the resultant vector, is equal to 13.4 centimeters. Now let's determine the total vertical, the y value of the resultant. You add this vertical to that vertical, and so we can do that very much the same way. The vertical side is equal to, it's called the opposite side, it's equal to the hypotenuse times the sine of this angle. So let's add up the vertical components. We have 40 times sine of 30, this vertical component, plus 30 times the sine of 135. That gives you 20 centimeters plus 21.2 centimeters for a total vertical component of 41.2 centimeters. So 41.2 centimeters. And so now we've determined our total horizontal by going over 30, 4.6, and then back 21.2. So our total horizontal is 13.4. And which you can see is right under the end of that last vector. And our total vertical is 20 plus 21.2, or 41.2, which we see is the height of the end of the last vector. And so that'll be, from the starting point, to do our resultant, we go over 13.4 and up 41.2. So we'll draw that in a separate drawing and finish up our math to determine what the magnitude and angle of our resultant vector is. Okay, so let me get rid of these old vectors. We don't need them anymore. We've determined an overall horizontal, let's start at the same place, of 13.4. So let me measure that out. 13.4, it's about to the right there. And then an overall vertical, we're going to make right angles, of 41.2. And so that's the same thing as going over here, then up there, or out here, up there, and over. Okay. We've simplified our path from the beginning to end to just east and north, horizontal and vertical. So now let's draw the resultant. And this resultant is the same place it was before. Going from start to the end, this is the resultant vector. It has horizontal of 13.4, vertical of 41.2. You can use the Pythagorean theorem now to determine the hypotenuse of this right triangle, because a squared plus b squared is equal to c squared. And from that we get the magnitude of the resultant is equal to 43.3 centimeters. Now, and of course, when you're doing this, be sure to show centimeters all throughout. I've been leaving off some of the units just to keep the board cleaner. Now the angle, this angle measured up, again we said it was around 70 degrees. Let's show you how to do that mathematically. Right angle trigonometry says that, let me call this theta. Theta is equal to the theta of the resultant. This is equal to the inverse tangent of the opposite over the adjacent side. So we're going to say is equal to the inverse tangent of 41.2 divided by 13.4. And that gives us the angle of the resultant as being around 72 degrees. So, using vector addition, we've determined the magnitude and the angle of our resultant vector when we added those two individual vectors. Now in today's lab, we have three parts. The first part, you're going to be using an online simulation to determine resultants of vectors. In the second part, there's going to be a coordinate system in one corner of the room that shows you x and y in the plane of the floor. And around the room, there's going to be three cards labeled 2A, 2B, and 2C. And for one or more of those, you'll determine the direction from the origin, or the resultant vector from the origin over to the card. Now part 3 is a little more tricky because the coordinate system also includes a vertical, or an up direction called the z-axis. And we have cards on the walls and the ceiling labeled 3A, 3B, and 3C. And you'll have to determine that three-dimensional vector, but I will give you a hint. It's a three-dimensional vector is really just the resultant of a two-dimensional vector plus the upward dimension. So it's really just adding two vectors together in a plane. So it's not as hard as it seems.